Now that we've seen what power series are about, we're going to see how to represent particular functions as power series. And as our foundation, we're going to consider the sum as n goes from 0 to infinity of r to the n, where the base r in magnitude is less than 1. As we know, this sum is equal to 1 plus r squared plus r cubed plus dot 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 plus, I'll throw in r to the n, but plus dot dot dot, it goes on forever, right? But as a convergent infinite geometric series, we know that this sum is equal to 1 over 1 minus r. So in the same way, we can express 1 over 1 minus x, where x in magnitude is less than 1, as the sum of a power series. All we really need to do is replace r by x. So 1 over 1 minus x is equal to the sum as n goes from 0 to infinity of x to the n, which is 1 plus x squared plus x cubed plus dot 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 on to infinity. I don't want what we've just done to be lost on anyone here. We've just represented a rational function, 1 over 1 minus x, that has a vertical asymptote at x equals 1 as the sum of an infinite polynomial. Now, we know this equality is only good if x is between -1 and 1. But in that interval, we can approximate this rational function by an nth degree polynomial. Here's what I mean. I've opened up Desmos.com and I've graphed y equals 1 over 1 minus x, and it's this red curve here, right? The reciprocal function. Down here you can see what we just wrote down, that 1 over 1 minus x is expanded as 1 plus x squared plus x cubed and so on. So I'm going to graph y equals 1. Now that's a horizontal line. It's a terrible representation, but we're going to add some more terms. Plus x squared plus x cubed. Whoops. And now you're seeing that as I add more terms around 0, right, between -1 and 1, we're seeing this blue curve, which is a cubic function, has a bend that much resembles that bend of the reciprocal function. Now I'm going to see if I can zoom in and recenter this a little bit. All right, now we're between -1 and 1 here, and we can see, as we saw before, that the blue curve is becoming close to the red curve. Now if I add some more terms, so plus x to the 4th, plus x to the 5th, plus x to the 6th, I know this is going to get old, but look, the more terms we add, the more the blue curve lines up with the red curve, but only between -1 and 1, right? I mean, over here, it's not really great for -1. But folks, this is only 6 terms, and we're talking about that this is expressed as an infinite polynomial. So this is what is meant by, we can now express this rational function, 1 over 1 minus x, as a power series, the sum of an infinite polynomial. That's what much of the rest of our work with power series is going to be about. And the foundation is going to be this particular function, 1 over 1 minus x. I'll show you what I mean. As an example, we're going to express 1 over 1 plus x squared as a power series. Now, when I see something like this, I am thinking of the one we just came up with, right? That we know how to express 1 over 1 minus x as a power series. So what I want to do is I want to convert 1 over 1 minus x squared. I'm not going to convert it into 1 over 1 minus x, but I want to convert it into that form. 1 over 1 plus x squared has some similarity to 1 over 1 minus x, but there are also some differences. One of them is that we have a sum in the denominator instead of having a difference. But we know how we can change that. I can express the denominator instead of 1 over 1 plus x squared as 1 over 1 minus the negative of x squared. Now I have this much of the structure, 1 minus and 1 minus, but now I have another difference here, and it's that I have a negative x squared here instead of an x here. The way this is going to play out is that we have 1 plus the negative of x squared plus the negative of x squared squared plus the negative of x squared cubed. What we're doing is we're replacing the base of x by negative x squared plus dot dot dot, and that will translate into a sigma notation that looks like the sum as n goes from 0 to infinity of negative x squared is the base to the n, which we can actually rewrite as the sum as n goes from 0 to infinity of negative 1 to the n, so we can see that the series is alternating, times x to the 2n, because we add x squared to the n. So I broke this up into negative 1 times x squared, and then expressed them as different factors, and here we see with this negative 1 to the n alternating x to the 2n, all of the exponents should be even. This is what we were after. I would recommend that you open up Desmos or GeoGebra or something and graph both 1 over 1 plus x squared and as many terms of this expansion, 1 minus x squared plus x to the 4th minus x to the 6th and so on, as you need to see that the two do align with each other as long as in magnitude x is less than 1.